I want to leave you with one more example of seeing if a function is continuous or discontinuous at a value. And let's look at a piecewise function. So we're given that f of x here is equal to the piecewise function. The first equation of that piecewise function is 3 minus 2x. And this is if x is less than 2. And we have x minus 3 if x is greater than or equal to 2. And let's find any discontinuity if it exists. Well, if you look at the first equation, that's a polynomial. Polynomials are continuous everywhere. If we look at the second equation, x minus 3, that's also a polynomial. So it's continuous everywhere. So really with the piecewise functions, what we have to be careful of is when it changes equations. And so it's going to change equations at x equals 2. And so we need to look at what's happening on the left of x equals 2 and at the right of x equals 2. And so looking at the limit, as x is approaching 2 on the left of f of x, this tells me that values of x I'm plugging in are smaller than 2, which means I have to use the first equation. So limit as x approaches 2 on the left is really the equation 3 minus 2x. And so plugging in direct substitution, we have 3 minus 2 times 2, or 3 minus 4, which is negative 1. Let's look at the limit as x is approaching 2 on the right of f of x. Well, those are values of x which are bigger than 2, so we need to use the second equation here. So limit as x approaches 2 from the right of x minus 3. Go ahead and do direct substitution. We get 2 minus 3, which is negative 1. So notice that my left-hand side and my right-hand side are the exact same. So my limit does exist, and it's negative 1. Okay, so that holds true for the piece that it has to have, the limit has to exist. If we look at f of 2, I'm sorry, it's continuous at that value, the limit has to exist. At x equals 2, so you have to go to which equation? It is the second equation because for x equals 2. So f of 2, I would plug this into my second equation, which is 2 minus 3. And 2 minus 3 gives us negative 1. So it does exist at that x value. And we just showed that that's the same value as the limit. So limit as x approaches 2 of f of x is the same thing as f of 2. So all three of the conditions held that had to hold in order for it to be continuous at that value. So because of that, we can say it's continuous at that place where it was changing equations, and because these are first equation is polynomial, second one is a polynomial, this is continuous everywhere. So f of x is continuous everywhere. Any questions on that?